then the meaning promised Grover, Simon, and Shaw. So this is the order in which we'll be going. So I really don't know like how much of fundamentals like this bracket notation, and then the postulates, and then what is the state space of a quantum system and all that, meaning whether it has been covered or not. So I put all that in this fundamentals, and then we go on to look at probably the first quantum algorithm which was given by Deutsch, and then there is a slight extension of it. And then we'll go to Grover's algorithm and look at an example. Probably that will be that for today. And tomorrow we'll be continuing with Simon and Shaw. So meaning in the next 1.5 hours, we'll be doing this much, I hope, with your cooperation. So yeah, let us go in. So let us just recall what is happening in classical computation. So we know that memory registers consist of classical bits which are in 2 states, 0 and 1. So meaning I just kind of want to tell you that there is this symbolism and notation. So I have followed some material which was written by a mathematician. So these people are not quantum physicists. So I just borrowed some material from meaning such a meaning that kind of a material. So you may see that most of the symbols and the notations will match with what is happening in the quantum computation domain, but there might be slight variation. For example, this mathbb is at 2 power n. So meaning I don't know, maybe people write it as 0 1 power n or something like that, but because this was written by a mathematician, so it's meaning they're following this kind of a notation. So this z sub 2, you can think of this as 0, 1. So that to the power n means you have n-bit binary sequences. So the usual operations like this bitwise OR, bitwise meaning and all these things are allowed. And computation, as we know, it consists of a sequence of functions of f from z2 to the power n to z2 to the power n, which transform the state of the system. So meaning if the register contains some meaning assignments like 1 0 0 1 0 1 like that, a computation will consist of a sequence of functions, right? For example, if you have a 1-bit function, the classical NOT gate, which is meaning the NOT of 0 is 1 and NOT of 1 is 0, right? So the NOT of I, you can write it as I plus 1 mod 2. So meaning just this is some kind of a structure to this classical computation, right? So this is what is happening in the classical computation scenario. We are not going into the much of computation theory per se, but just to draw the parallels. Okay. So what is happening in quantum computation? So the memory of a quantum computer is a finite dimensional complex vector space with the inner product. And meaning this okay, so this V stands for this finite dimensional complex vector space. Okay. So sorry, meaning I think the first sentence is somewhat misleading. So what I want to say is that so you have a finite dimensional vectors complex vector space which is endowed with the inner product, and I'm calling it V. So the memory of a quantum computer is this space V. Okay. So a state is a unit vector in V. So these are the terminology which will keep appearing over and over again. So the memory is a complex inner product space V. State is a unit vector in V. And meaning again, let us just meaning kind of swallow this notation. So this will appear everywhere in this talk. So this mathbb cx, by this we mean a complex vector space generated by x. Say for example, meaning if you think of this polynomial ring, you can polynomial ring. Sorry, if you think of this polynomials 1x x square, sorry, 1t t square up to t to the power n minus 1. If you look at complex linear combinations of this 1t up to t to the power n minus 1, this forms a vector space, right? So you can add 2 polynomials, and if you multiply this polynomial by a meaning complex number, you get another polynomial in the same set, right? So the degree does not change, meaning I'm not allowing multiplication. I'm just adding polynomials and I'm multiplying polynomials by a scalar, which is coming from C. So in that sense, by Cx, we mean that it is a complex vector space with the finite set X as basis. So keep in mind that we have such a description, meaning one example is this X is equal to 1t up to t to the power n minus 1. And you're taking complex linear combinations of this n polynomials. So that gives a complex vector space. OK, so a n qubit quantum computer. So what we had in the classical, we called it bit, and when you come to quantum, it is qubit. A n qubit quantum computer has memory consisting of 2 to the power n dimensional vector space v equal to c z to the power tensor power of n. So meaning, let us just swallow this notation. So this will come later. So we will have a 2 to the power n. So if you have n qubit system, so you will be working on a 2 to the power n dimensional vector space. So the simplest being, if you have a 1 qubit system, you will be working on a 2-dimensional vector space. Meaning 2 qubit system will have a 4-dimensional vector space. 3 qubit, you will be on an 8-dimensional vector space. So you will have a basis respectively of size 2, 4, 8, and like that. OK, so a n qubit quantum computer will have a memory which will be the complex vector space V, which will be spanned by 2 to the power n vectors. OK, so see that there is an exponential blow up in the sizes. So n qubit corresponds to 2 to the power n dimensional vector space. OK, so this vector space is the same as the usual vector space of dimension 2 power n. So we'll see that that is the case, but it has a different inner product. So we'll come to that again later. So we can see that compare and contrast is that classical, you will have registers with bits 0 and 1. And then meaning computation is a sequence of functions. Here we have the memory, or the meaning the operational space of this quantum computer is a complex vector space with a inner product, finite dimensional, and then state of a, meaning we can talk about state of a classical computer also, right? Turing machines and all that we talk about. Similarly, here a state is a unit vector in this vector space V. Just a notation, Cx means it's a vector space which is generated by this finite set X as basis. So a n qubit quantum computer will have memory in 2 to the power n dimensional vector space. So we'll describe this wheel sometime later. So meaning dimension wise, this is the same as a complex vector space of dimension 2 power n. So we have this very famous theorem, right? So if you have a field, whatever field f, n dimensional vector space is a n dimensional vector space. There is not much difference in the structure, right? So all these things are isomorphic, we say. So meaning we know that this V, which is meaning this n qubit quantum computer's memory, it's a 2 power n dimensional vector space, and there is only one 2 power n dimensional vector space. OK, but meaning the thing is that this will have a slightly different inner product. So we'll come to that inner product business sometime later. So a quantum computation, as we know, it has 3 phases. One is this input, second is this evolution, and third is this measurement or output. OK, so 3 phases: input, evolution, measurement or output. So input states, you need to prepare it. So like it is not as easy as meaning C in command as in the classical C++ language. This you need to prepare this input states. All these things are dealt with by the experimental physicists who tell how to feed in this. Meaning if you have access to say some IBM computer, so meaning there will be some internally things will be working in such a way that the states will be prepared and then the computation will proceed. OK, but we will not be going into the specifics of how the states are prepared, etc. OK, so let us come to the next phase, which is evolution. So evolution consists of a sequence of unitary transformations. So again, this unitary business I will come later, but at the meaning top level, what we have is that we have a vector space. So a unitary transformation is first of all a linear transformation. You can think of it as meaning matrix which is mapping V to itself with some specific properties. OK, so what is this unitary business will come later. So evolution consists of sequence of unitary transformations. So these are not just any transformation, but they need to be unitary. So there is some logic behind it. We'll come to that later, but we will not dwell deeply into why it's and wherefores of this unitary business. OK. So, for example, if you identify Z2 with the usual basis vector E0 and E1, so what is that? Meaning the 0 bit and the 1 bit. The quantum NOT gate will say, for example, take this alpha E0 plus beta E1 to beta E0 plus alpha E1. OK, so it is just kind of permutes the basis elements and gives this meaning. So E0 will go to E1 and E1 will go to E0. So just a quantum extension of the classical NOT gate. OK, so this is not some standard quantum gate as we know it. I just want to give an example that classically you have a 0 going to 1, 1 going to 0 map. So what happens in the quantum sense? So you map this 0 bit to this E0 vector on 1 bit to this E0 vector, and then look at this two-dimensional vector space. So that meaning which is given by this MathBB's Z sub 2. So any vector is a form alpha E0 plus beta E1. It's a linear combination, right? So that will go to beta E0 plus alpha E1. So at the basis level, E0 is mapping to E1 and E1 is mapping to E0. So there is this permutation. OK, just an example. So yeah, quantum extension to a classical gate. So what does a measurement do? Measurement transforms the state. So the process is probabilistic rather than non-deterministic. So yeah, measurement will take a vector in this vector space and it will output a classical sequence of bits. OK, you can think of it that way. A measurement will take a vector from this vector space and output a classical bit string. OK, and the process is probabilistic. So if you take a measurement of a vector, it will with probability give you this. It will give a with probability will give you this. So there will be a distribution on the output sequence. OK, and the process is not meaning in some sense non-deterministic. It's probabilistic. So with there is a meaning fraction of times certain thing will happen. So you can always be assured that there is at least a fraction of times a certain measurement will be measured. OK, so that is what is meant when we say the process is probabilistic rather than non-deterministic. So let us go to Dirac notation and some linear algebra. So we work in, as I said, finite dimensional complex inner product space. So state is a unit vector. Sorry, this has to be a unit vector in such a space. So by superposition, we mean a linear combination of the given vectors. OK, so we need a unit length linear combination of the given vectors. Say, for example, if you are given E0 and E1, so if you take a, for example, the usual thing is if you look at this uniform superposition, so you can think of this as E0 plus E1 by square root of 2. So meaning if you take the meaning square norm of this, meaning the L2 norm of this, you will get this is of length 1, right? So meaning 1 by 2, 1 plus 1, that gives 1 by 2 times 2, square root of it is 1, right? So like that, superposition is a linear combination. So amplitude is a coefficient of a vector expressed in terms of some fixed basis. So if you look at say uniform superposition E0 plus E1 by square root of 2, amplitude of E0 is 1 by root 2, amplitude of E1 is 1 by root 2, right? So this uniform superposition, and there is some other terminology also which will appear later. So this means that all the amplitudes are equal. So like this, like meaning you can have meaning various unit length vectors, right? But the uniform superposition is the one in which all the meaning all the basis elements appear with the equal amplitudes. If you express it in terms of a standard basis. OK. So here comes this the very famous notation introduced by Dirac. So meaning this is not different from what we learn in the classical mathematics courses in linear algebra. It's just that this quantum mechanics and computation has its own set of kind of symbolism. So there is nothing to be afraid of this. I'm sure that most of you have seen this and quite familiar with it also. So the first thing is called ket, which will denote vectors. OK, so if you take a complex inner product space, it will have vectors, right? So the ket will usually denote vectors, and in particular, if you're talking about a space, a state of a quantum system, we need that to be a unit vector. So we talk about ket of psi, for example, where psi is a state. So state will be a unit vector in that underlying space, which will be a complex inner product space. So n qubit system will need a 2 to the power n dimensional complex inner product space. So for example, 3 qubit system, you will have a vector in 2 to the power 3, which is 8 dimensional complex vector space. So it will have 8 components, right? So you'll have a meaning if you write it in terms of a basis, you will have a vector which is having 8 entries. Okay, so that is enclosed in within this meaning vertical bigger than, so that is called the ket notation. So the dual of it, so whenever you have a vector space, you talk about the dual, right, which is set of all linear functionals. So these you can think of as meaning in the classical linear algebra terminology, these are transformations which take vectors and map them into the underlying field. So in this case, complex numbers, and which is also a linear transformation. So these, when you look at this set of all functions which map from V to the underlying field C, so this again forms a vector space called V star, the dual of the vector space, and meaning with every A belonging to V, there is a natural way of assigning A star in belonging to V star, and that collection of all A stars will be denoted by this Braun notation. So which is a dual of this vector V, okay, which is actually a functional. Okay, we'll come to this, explain this a bit later. Okay, so if we have a set meaning set of all x such that x belonging to x, so this is the orthonormal basis for Cx with the usual inner product. So normally in this quantum computation, what will happen is that you take this 0 up to n minus 1. So for a n qubit system, you have this, right? 0 up to n minus 1. Sorry, for a, I'm sorry. So this is a bad notation again. So actually this is 2 to the power n. So in some sense, so we have 0, 1, 0, 1 for the 1 qubit system, 0, 1, 2, 3 for the 2 qubit system, 0, 1, 2, 3 up to 7 for the 3 qubit system, and so on. So 0 up to n minus 1 is the standard orthonormal basis. So for example, you go up to 0 up to 2 to the power k minus 1 for some k, where k is the number of qubits which is there in that meaning underlying system. So actually this is a bad notation, meaning I was using this n for n qubits, but this is actually corresponding to that old 2 to the power n. So this is 2 to the power n in some sense. Okay. So the complex inner product between two vectors V is explained via the dual. So usually how do you take, if you have x1, x2 up to xn, y1, y2, y up to yn. So in the real meaning real number scenario, you have x1, y1 plus x2, y2 up plus and so on till xn, yn. So here, because we are in the complex meaning domain, what we have to do is we have to take the the conjugate of the first vector and this linear in the second vector. So this is x1 bar y1 plus x2 bar y2 plus and so on till xn bar y. Okay, so meaning by bar we mean this complex conjugate, right? So meaning a plus ib has this complex conjugate, right? So we go to that complex conjugate and then compute its inner product between the two such vectors. So we see that, the one thing we have to remember is that it is linear in the second variable and conjugate linear in the first, right? So it's conjugate linear in the first. So if t from v to w is a linear operator, then x, t, y, so which is enclosed inside this, will denote the inner product between x and ty, right? So if you have a t, which is a linear transformation, which is mapping v to w, so a linear operator x, t, y denotes the inner product between the ket of x and t of y. So notice that if you have y belonging to v, so ty will go to w, and w meaning x is a vector in say w. So the ket of x and t of ket of y, both of them end inside this w. So it makes sense to take the inner product between these two things, which is defined in the previous bullet, right? So if we have an orthonormal basis ket of v1 up to ket of vm and ket of w1 up to ket of wn, for the orthonormal. So V is a m-dimensional vector space and W is a n-dimensional vector space. So we have basis ket of V1 up to ket of Vm for V and ket of W1 up to ket of Wm for W. So these are orthonormal bases in the sense that meaning only the same indices will survive and the other indices, if you take the inner product, will be 0. So the same indices, when you take the inner product, that will be 1, and both these are bases. Then the matrix with Wi T Vj. So if you compute this meaning this ijth entry, so and then put it inside a matrix. So ith row jth entry is Wi T Vj, which is how it is computed is given in the previous bullet. So that will be a matrix representation for this T. Okay, so we know what is a linear operator now and how to write it in terms of the basis for V and W if you are given a orthonormal basis, which meaning in short form you say ONB. So if you have a ONB for V, ONB for W, we know how to compute Wi T Vj. So if you collect all these ijth entries and put it inside a matrix T, that will represent, sorry, put it inside a matrix that will represent this T, right? Okay. Now, the next thing which we have to learn is about this adjoint. So we said that V star is a set of all linear functionals. So we can talk about V star star. So in basic linear algebra, we learned that V and V star star there is a canonical isomorphism between them. So this is defined via this T dagger. So the meaning I say T dagger, which is the notation for this adjoint of T. So definition is that of adjoint of T. It's a unique linear operator which is given as T dagger of the ket of x. So this gives a function. So that of y is equal to x Ty. Okay, so T dagger of x evaluated at y is x Ty. So this is a definition. So this is a map from V star star to V. So there is a natural this gives a natural isomorphism how to identify V star star with V. So this will appear everywhere in this whole domain of this meaning quantum computation. Okay, so those of you who are more familiar with matrices, you'll see that this is the conjugate transpose because we have entries from the complex numbers. So the matrix corresponding to T dagger will be you take the matrix of T. So we have the we are computing the adjoint of a linear operator T. So the adjoint of T will have entries coming from C again. So how do you compute it in terms of matrices? You take the conjugate transpose. So every element you conjugate first and then take the transpose of that matrix. Okay. So we say that T is unitary if and only if T commutes with its T dagger. So T dagger T is equal to T dagger equal to identity. So recall that meaning in sense of quantum computation, we need to prepare the state and then allow it to evolve. So evolution, we saw that it was a sequence of unitary operators. So I said that it is first of all a linear transformation between from V to V. So but with certain other properties. So that property is that it is commuting with its adjoint. So T dagger T is equal to T dagger equal to identity. Okay. So if we regard this meaning, like I said, so how do you kind of define a linear functional for a vector ket of x? So if we regard this ket of x as a linear operator from C to, oh sorry, it's the other way. Sorry, yeah. If we regard this ket of x as a linear operator from C to V, taking 1 to the meaning, yeah, taking 1 to this ket of. So how do you embed C inside this V? So the dual of this linear functional is the bra of x, which is ket of x adjoint, taking y the inner product between x and y. So the dual is a linear functional, namely the bra of x is equal to this meaning the ket of x, the transpose, the conjugate and adjoint of it, taking this y to x inner product y. Okay, so X is a linear operator from C to V. The dual is a linear functional taking Y to the inner product between X and Y, right? So which is just the how is it operating? It is operating as the adjoint of this X. Okay. If V and W are vector spaces, X coming from W, Y coming from V, then we can talk about the ket of bra. So this will be a linear operator defined by meaning ket of X. So we apply, we first of all compute the inner product between Y and V, and then the value of this ket of X bra of Y at V is the inner product between Y and V times this ket of X vector. So notice that this bracket of YV is a scalar, a complex number, that multiplied by this ket of X is the answer to this ket of X bra of Y of V. Okay. So in fact, this W dagger denoting the dual of W. So the map meaning ket of X bra of Y, you can think of it as a bilinear map, which is mapping from V cross W dagger, meaning I think this notation is actually it has to be W star star. So you can think of it as W star star. So meaning in terms of matrices, you're looking at all those meaning we can think of this as the element of this W dagger is, you can think of it as this small W dagger, right? So the ket of small W dagger. So which will be sending this meaning pair of vectors V, the ket of V bra of W to W inner product X times Y inner product V, which is an element of C. Okay, you can think of this as this bilinear map. Okay. So let us come to the meaning the concrete kind of calculus which is required for doing n-qubit calculus quantum computation. Okay. So usually what we do is we have classical strings, right? Bits of zeros and ones, and the output also we need it to be classical, so that we need to first encode this classical information in terms of quantum, and then allow it to evolve, and then we measure and get the output. So that is the flow, like that is what we saw. So the first step is to identify. So this is an example of the first bullet is corresponding to a one qubit system. So recall that you have to operate in a 2 to the power 1 dimensional vector space. That is a 2-dimensional vector space. So if you identify 0 with 1 0 transpose, meaning this capital T I'm using to denote the transpose. So usually I like to write the vectors column wise. So this ket of 0 is the column vector 1 0 and ket of 1 is this column vector 0 1. So meaning you identify this classical 0 1 bits with these two basis elements. Okay. Then we define what is called the tensor product of two such CZ2s. So CZ2 tensor product CZ2. So this is a 4-dimensional vector space. You can think of it as meaning two classical bits appearing together. So 0 0 0 1 1 0 1 1. So in some sense you can think of all the numbers from 0 1 2 3, and you look at meaning some way of identifying this as a basis of this inner product space CZ2 tensor product with CZ2. So this is an example of a 2-qubit system which will have dimension 4. So having identified this 0 and 1 as this 1 0 transpose and 0 1 transpose vectors respectively, we have this basis 0 0 0 1 1 0 1 1 naturally, like meaning how we meaning usually do it. So this 4 basis elements will give you a 4-dimensional the space spanned by these 4 basis elements will give you a 4-dimensional vector space. Okay. So generally what happens is you take bit strings 2 to the power n dimensional meaning complex vector space. So how do you generate it? So you have to look at 0 up to 2 to the power n minus 1. So meaning you start with 0 0 0, go on up to 1 1 1. That 2 to the power n bit strings you identify with this vectors, and this set of elements will give a what is called a standard basis. So I think they also call it computational basis for this entire quantum computation scenario. So meaning there is, so this has to be somewhat clear in the sense that we have to take for a n qubit system, you have to take meaning bit representations of 0 up to 2 to the power n minus 1. So for a 3 qubit system, for example, you have to look at 0, 1, 2 up to 7. So which is 0, 0, 0, 0, 0, 1, 1, 0 like that, and going on up to 1, 1, 1. Similarly for a 4 qubit thing, for a n qubit thing. So this forms a basis for this meaning entire computation. So this is the thing which is going to keep appearing throughout this two talks. Okay, so we have to be clear about it. So the usual tensor product. So 0 and 1 we have identified like this. So 0, 0, 0, 1, 1, 0, 1, 1 gives a basis for your 4-dimensional vector space, which is tensor product of these two meaning 1 qubit things. So like that, we can extend it to the n qubits via looking at the bit representations of integers ranging from 0 up to 2 to the power n minus 1. Okay, and usually this is also stated everywhere like this ket of v tensor ket of w. So we short form this and write it as ket of v ket of w. In some cases ket of vw. Okay, so all these three things mean the same. So by the 0, 0 meaning in the second bullet I put this ket of 0, 0, right? So this means that we are taking the tensor product of this ket of 0 vector with itself. So we know how to take the Kronecker delta of these two matrices, right? So this ket of 0, 0 means that. So you're taking the Kronecker delta of ket of 0 with itself. Okay, so that is being captured in this fourth bullet, where I say that there is some shortening in the notation where I say that v tensor w, you write it as ket of v ket of w, sometimes ket of vw. Okay. So if m and n are complex vector spaces, then m tensor n can be when you do an inner product space. So we have a inner product on m, we have an inner product on n. So any element like this a tensor b inner product with c tensor d, it's enough to define here. Then we can take linear combinations. So this is the value of this is a tensor c, so which is a complex number multiplied with b tensor d, right? So this is the inner product. The first one is a complex number which is obtained by taking inner products on the m vector space, and the second one is a complex number b inner product d is a meaning complex number which is obtained by taking inner product on the complex inner product space n. Okay, like that we can extend it to n meaning it's very bad notation. Actually, I should have put capital N at least. So if you have this x which is given as a bit representation x1 up to xn, y which is a bit representation y1 to yn, then we can take the n4 tensor product as this product of xi inner product yi. Okay, because the cross things will vanish, and meaning this is how the tensor product is in some sense defined. Okay, we just extend this previous bullet to n such meaning n vectors. Okay, so so this gives you what is the tensor product of two matrices. So we have a linear transformation theta from v1 to w1. We have psi, which is a linear transformation from v2 to w2. So these are linear transformations having matrices a and b respectively. So these can be of meaning any dimension. So there is no restriction like in the so we can multiply only matrices of a certain shape, right? But here there is no such restrictions. So theta is any linear transformation. v1 w1 there is no restriction on the dimension. Similarly, psi is a linear transformation. v2 w2 there are no restrictions. So a and b are the corresponding matrices. Then we know how to compute the meaning the Kronecker product or the meaning theta tensor psi. So which will be a linear transformation from vn tensor v2 to v2 tensor w2. Sorry, this is bad. v1 tensor v2. This has to be w1 tensor w2. Sorry, this has to be w1 tensor w2. So which is obtained using the usual Kronecker product. So if you have a equal to a11 up to a1m, an1 up to anm. So for each it's given as this block matrix. So I don't think I'll read it out. So a11b up to a1mb, like that, an1b up to anmb. So this is given in that block form. Okay. So let us go to what are the postulates of this quantum mechanics. Like I said, this is from a purely linear algebra and mathematics point of view. So there is no meaning there is no inquiry into why these postulates hold. So this is for the physicists to think about, and meaning I don't know much about why these things come about. So I just want to capture, like in the usual whatever quantum computation courses I have seen. So this is how they capture it. So we are just talking about the maths behind the quantum mechanics and quantum computation. So whatever meaning whatever kind of assumptions we need to make on make so that our quantum computation proceeds. So those things are captured as postulates. So the first postulate says that any isolated quantum mechanical system. So with that, we can associate a complex inner product space V. So that was the first motivation for looking at complex inner product spaces. So we saw that we can take a basis element as bit strings from 0 up to the power n minus 1, and then so which is a n-dimensional, and then you can define a n-dimensional complex vector space using this kind of a representation. So the motivation for that is that the first postulate of this quantum mechanics says that any isolated quantum mechanical system is associated with a finite dimensional complex inner product space V. Okay, so the state of any system at any time is the state of such a system at any time is described by a unit vector in V. Okay, so for a single qubit, I've just given some examples. So a single qubit system with 0, 1 as basis, like we saw that this ket of 0, we had this 1, 0 vector as a read as a column, and ket of 1 is the 0, 1 vector read as a column. The state is alpha ket of 0 plus beta ket of 1, a linear combination of these two things, such that meaning the absolute value or the absolute value of this alpha square plus absolute value of beta square. So recall that these are complex numbers. So you have to think of this as the complex absolute values. The sum of this square is equal to 1. So we just say that the usual meaning L2 norm in some sense. OK, and then we can think of this uniform superposition where this alpha and beta should be equal. So that says that alpha equal to beta equal to 1 by square root of 2. So you will always see this 1 by square root of 2 to the power n appearing everywhere in the next slide. So that is the motivation. So the thing is uniform superposition. If you assume that it is a meaning single qubit system, you are in a uniform superposition kind of situation, then alpha should be equal to beta, and 1 by square root of 2 is the common value, right? And so we can read off the amplitudes also. So amplitude of 0 will be alpha, amplitude of beta, 1 will be beta. So recall that the output of a quantum computation is again a classical string. So a n bit string is 0, 1 up to the power n minus 1. Think of that as an integer as well as the binary equivalent of it. So a measurement will give you a basis vector, and with that there will be an amplitude sticking with it. That will be the measurement of a meaning quantum system. That is the output also. Okay, so the output is meaning the output of a quantum computer is a n qubit classical string. So you can think of that as the meaning after doing some kind of a calculus, you can think of that as the amplitude of some basis vector. That is how things will usually proceed. And meaning I just want to point out that you can read off the amplitudes by looking at such a linear combinations. For example, the amplitude of 1 in this linear combination is beta, and amplitude of 0 is alpha. Okay, so after doing a measurement, you will get a scalar times a basis element. That scalar will be the output of your quantum computation. So a simple extension, you can get n qubit systems. So we say that quantum mechanical system, the state space is a complex inner product space. A state of a system is always a unit vector. Okay, so these are the two bullets of this first postulate. Second postulate, the evolution of an isolated quantum mechanical system is governed by a unitary transformation on V. So we recall that there is this T dagger business. So T dagger T equal to T dagger equal to identity. Such a transformation is called unitary. So the evolution, which is a second state in a second phase of a quantum computation, is governed by this a sequence of unitary transformations on V. Okay, so we can compose it and still get a unitary transformation. So that is later, but you can think of this evolution as a sequence of unitary transformations on V. Okay, so if we have the you take a snapshot of the quantum mechanical system in some sense at some time. So if you observe this that the state is V1, and I mean, of course you cannot do it physically, but I'm just saying that if the state is ket of V1 at some time and ket of V2 at some other time, then this ket of V2 is the image under the unitary transformation phi. That you can always find such a unitary transformation phi such that ket of V2 is equal to phi meaning the image of ket of V1 under this phi. Okay, you can always find a unitary such that ket of V2 equal to phi of ket of V1. Okay, in the context of quantum computation, evolution of the system takes place at discrete intervals of time. So there is no continuous process. So you can think of it as, so meaning there is no need to integrate. There is only a summation which is required. So evolution takes place at discrete intervals of time. So this is another kind of assumption which you make. So there is no continuous unitary transformation of the state. There is only discrete. So the state of the system changes only at discrete intervals. Okay, and finitely many times, each according to a unitary rule. So that is how the postulate, that is what the postulate is saying. Okay, so this evolution, you can think of it as computation. So basically, you can think of this set of gates like this AND gate, NOR gate, meaning NOT gate, etc. So we have a set of classical gates which can be used to build any circuit, right? So like that, there is a set of quantum gates which you can use to build unitaries. Okay, so meaning how efficiently and all that comes later, and meaning that will be the main focus when we talk about most of this algorithms. So quantum gates exist, and many unitary transformations can be computed using this quantum gates, right? Okay, that is what I want to say. So third postulate is regarding measurement. So I'll just skip this slide because it's not too relevant to our later discussions. So the measurement system consists of linear operators like this, such that summation m equal to 1 to k, dagger equal to identity. So I just want to point out that so there is something called projective measurements. So second bullet alone is sufficient for us. So these are self-adjoint in the sense that composed with itself will be and composed with mn equal to 0 for m not equal to n. So you can think of this set of measurements as giving a decomposition of the underlying vector space as summation, meaning direct sum, summation over m of vm, and you can think of this mm's as projection onto this vector subspace vm. So we can decompose this v into summation vm, and this is a projection onto that subspace vm. Okay, so this is sufficient for us, and the third bullet is important. So we think about this computational basis, so which is the ket of m. So you think of this integers ranging from 0 up to n-1. So again, bad notation. 0 actually I should have written 2 to the power n-1. So n qubit system corresponds to 2 to the power n-1 dimensional vector space. So you look at strings from 0 up to 2 to the power n-1, and you write it as meaning bit strings. So that gives what is called a computational basis for this meaning entire process, and the measurement will be of the form ket of m, bra of m. So we defined this earlier, right? So any will look like this. So you can think of this as projection onto this corresponding vector subspace. Okay. And the last bullet probably it's not going to appear. So let us just skip it. So fourth postulate is coming to this tensor product business. So we have two quantum systems. So with one system you associate V, with the other you associate W. So this composite system, so you can think of that as the basic space where you have to operate is V tensor W. So that was the motivation for defining this V tensor W. So if we have V and W corresponding to two quantum systems, then the composite system, which is the sum total of both these quantum systems. So the state space is going to end up in this tensor product of V and W. So we can, in some sense, extend it. So we have already seen this, right? So we can extend this to any finite number of systems. So if you have a 2 power n dimensional complex vectors, so if each of you are, so how do you get a n qubit system from a 1 qubit system? So you kind of replicate it 2 to the power n times, and then you take the tensor product. So that is what this second bullet is saying. So look at strings from 0 up to the power n-1, and look at this keta phi, where I is ranging from 0 to the power n-1. This gives a basis for your vector space, and that is where this n-qubit system is going to operate. Okay, so if we have m-dimensional VM, n-dimensional Vn, then Ij. So usually which is defined as the Kronecker product. So you can think of this I as a column vector, J as a column vector. Take the Kronecker product of this I and j vectors. Then this keta phi j, where I is ranging from 0 to the power n-1 and j is ranging from 0 to the power n-1. This gives a basis for this VM tensor Vn. So if you have a m qubit system and a n qubit system, how do you get a mn qubit system in that sense? So we take all the ij's, and then we look at this meaning I ranging from 0 to the power m-1, j ranging from 0 to the power n-1. So this keta phi j gives a basis for this tensor product. Okay, the usual way. So I think this is also not required. So what this says is that if you measure once and then you measure again, so it's equal to putting one measurement. Okay, so let us not go into this. And I think this is also not required today. So the no cloning theorem says that it is easy to copy the contents of register into the another when you have a classical thing, right? So when we do swap of x comma y, a bad programming thing will kind of store this x into some temporary register and then copy that y into this x register and then assign this temporary register this y, right? So in naive swapping kind of a thing. But that is not allowed in a quantum system. So you cannot copy a state of a quantum n-qubit system. So that is what is captured by this no cloning theorem. So this is not required for us, but I just put it here. And then the main thing is this entanglement. So all these things will come into the meaning when we look at QKD, for example, we talk about QKD of entangled qubits. So in that sense, this would arise. But you can think of this entanglement as, so if you go to this V tensor W, not every vector is of the form small x is equal to V tensor W, right? So we have to look at linear combinations of this. So that is how the tensor product is defined. So when we for a state x which is coming from this V tensor W, if there are vectors V and W such that x is equal to V tensor W, then we say that x is disentangled. So that is, meaning in some sense, meaning I'm not sure whether it is correct physically. You can think about this state x is you can study it separately as a component of V as a component of W. But the state is more complicated than this. So you will have linear combinations of V8 tensor Ws. That is how a standard or meaning the usual state of this V tensor W will look like. So if you take any vector from V tensor W, it's a summation alpha I V8 tensor Wi, right? So that is how a random any element of this X will look like. Sorry, any element of this V tensor W will look like. But if we can find this V and W such that X is equal to V tensor W, we say that it is disentangled. Otherwise, it is not disentangled. So a simple exercise for all of us is that if you have a 2 qubit system, you look at this ket of 0 0 plus ket of 1 1. So you meaning it's somewhat pretty easy to prove that this is entangled. That is, you cannot find a V and W such that this ket of 0 0 plus ket of 1 1 is equal to V tensor W, where V is coming from a 1 qubit system, W is coming from a 1 qubit system. Okay, so that is an easy exercise to complete. So the main hero of this entire story is this Walsh-Hadamard transform. So this is going to come time and again. So I just want to define it as a single qubit Walsh-Hadamard transform. So I'm not defining. It's the usual way how it is defined is that a single qubit Walsh-Hadamard transform is a unitary operator W, which is operating on a single qubit system given by this. So recall that meaning ket of 0 was this column vector 1 0. So it is taking this 1 0 vector to 1 by square root of 2. Ket of 0 plus ket of 1. So ket of 0 was 1 0, ket of 1 was 0 1. So 1, you can think of this as 1 by square root of 2 1 1. That is a vector, right? And ket W, how is it mapping 1? It is taking it to 1 by square root of 2 ket of 0 minus ket of 1. So recall that ket of 0 was column 1 0 and ket of 1 is column 0 1. So ket of 0 minus ket of 1 is 1 minus 1 written as a column vector. So W of ket of 1 is 1 by square root of 2 1 minus 1 as a column vector. Okay, so so the second bullet is going to appear time and again. So let us just kind of record this. So if we have W, if you look at the image of that under so the first thing I should say is that you can extend it to a n qubit thing. So how I put it here. So I think this should come later anyway. Sorry, let's just forget about this first bullet. So we have the fact that W is an involution. So forget about the first bullet for the time being. We'll come to that later. So first bullet, the second bullet is saying that this Walsh-Hadamard transform is a involution, namely that if you apply W once and then W again, you get the same vector. So this you can verify. So first you take W of ket of 0, which will be 1 by square root of 2 1 comma 1 vector. If you apply meaning W again, you will see that you will get this 1 0 vector again. So I'll just hand wave and say that you can easily verify, at least for the 1 qubit system, immediately that W composed with itself will give you identity. Okay, so how do you extend this Walsh-Hadamard to a n qubit system? So that is important. So meaning we know that this tensor product. So again, there is this notation which you just bring in. W sub n, we write this as W tensor W dot tensor W n times. So that is also W written as tensor power n. So this is standard notation. So the ket of 0 tensor power n will be ket of 0 tensor ket of 0 ket of tensor ket of 0 n times. So this we can do using Kronecker product, right? So this is 1 0 tensor 1 0 tensor 1 0 n times. So this we can compute as block product of the Kronecker product of block matrices, right? So this we can define. So this we can. So I just want to hand wave and say that if you take this WN Walsh-Hadamard transform on this n qubit system, so it will put the 0 0 0 that ket of that vector in uniform superposition. So you can see that in most of the quantum algorithms, the first step is taking the 0 0 0 vector and applying Walsh-Hadamard and putting it in the uniform superposition. So the the first thing I should say is that we can extend this Walsh-Hadamard transform to n qubits. So we know how to do it. And then if you apply this Walsh-Hadamard and this uniform, if you apply this Walsh-Hadamard on this 0 0 0 vector, that will give you a uniform superposition of all this to the power n minus 1 vectors. Okay, so I think, sorry, this is a mistake. So 1 by square root of n x is equal to 0 to the power n minus 1. Okay, sorry, this is a mistake. So so there is a very easy computational formula. So this formula we have to remember. So if you have this ket of x, which is there in this n qubit system, so when we apply Wn on this, so calculus wise, this is giving you a formula. This is equal to 1 by square root of n summation k equal to 0 to the power n minus 1 minus 1 to the power x dot k. So this is the usual. So what we have is that we have a bit representation of this x, the bit representation of this k. We take the meaning as you take the inner product. The dot product means you're just taking the xi with ki, x1 with k1 plus x2 with k2 plus x3 with k3 and so on, xn plus kn. So x dot k is that actually. So x is a you write this x as a bit representation, right? You write this x in a bit representation, k in a bit representation, and you just take the usual inner product. So there's no complex business there. So inner product as 0 1. So inner product between 0 1 strings. That is all. Okay. So let us just kind of freeze this formula. So we define this Walsh-Hadamard on a 1 qubit system. So there is a natural way of extending it. So I just hand waved there for an n qubit system. But what is the effective kind of a thing which we need is this formula, namely that Wn, it operates on x in the following way, ket of x in the following way. You take 1 by square root of n summation k equal to 0 to the power n minus 1. So you're in an n qubit scenario. Minus 1 to the power x dot k. So times the ket of k. So x dot k is the usual inner product. So there is no complex business here, like I said. So you write this x as a in the bit representation in terms of zeros and ones, k in zeros and one bit representation. So xi ki sum it over meaning all the indices, right? So that is the way this wn of this ket of x is computed. Okay. And meaning why does quantum give you such a speed ups? So we saw that a quantum computer has advantage in terms of the time complexity. So that is the usual main bullet for promoting quantum computation, quantum computing, building quantum computers kind of a research. So the main thing is that if you have any classical function, so this is again going to come everywhere again. So this is captured by the phrase quantum parallelism. So whenever we have a classical function f, which is operating from m classical bits to k classical bits, you define this unitary u sub f. So this is going to take this meaning m tensor space. So sorry, yeah, see the 2 to the power m dimensional vector space, which is the first one, and 2 to the power k dimensional vector space is the second one in the tensor product, and takes it to the same thing again, which is defined as follows. So you take this uf, when you apply it to ket of x tensor ket of y, you get ket of x tensor ket of y XOR f of x. So this O plus notation which you have put here is the usual bitwise XOR. So recall that meaning the basis is set of all numbers from, you can think of this as positive integers from 0 to 2 to the power n minus 1, to the power n minus 1. So this has a bit representation. So this y is a bit vector 0 1 1 0 1 1 1 0 1 like that, and f of x is again a bit vector of the same length. So we can take the bitwise XOR. So this UF map is a unitary which will take meaning this 2 to the power m dimensional vector space tensor with the 2 to the power k dimensional vector space to this m dimensional 2 to the power m dimensional 2 to the power k dimensional tensor product. So how is it operating? So if you take ket of x from this the first argument, ket of y from the second argument in the tensor product, so you can extend it linearly, right? So for this kind of vectors, so UF will not operate on the first one. It'll just take the ket of x to the ket of x, and the second operation, second kind of the argument becomes the ket of y XOR f of x. Okay, so this is, so there are various names for this. So one is the standard oracle probably, and the standard unitary operator UF. So some of them call it oracle O. So this is going to appear everywhere in the domain of quantum computation. So so we can verify that this UF is unitary. So what this says is that if you have any classical function, you can kind of simulate it on the quantum computer. So you use this F to define this oracle. You go to the 2 to the power m tensor 2 to the power k dimensional complex vector space, and then you use this unitary. This way you can simulate any classical function on a quantum computer. Okay, so let us just ignore the other two. So the upshot is that we can simulate any classical computation on a quantum computer via this UF oracle. So which is operating on this 2. So if f is m bits to k bits, so you take a 2 to the power m tensor 2 to the power k vector space complex in a product space, and then this UF is defined as UF of ket of x tensor ket of y is equal to ket of x tensor ket of y XOR f of x, which is just the bitwise XOR. So this defines a unitary operator, and we can hence conclude that we get a simulation of a classical function on a quantum computer. Okay, so this is usually captured under the title quantum parallelism. Okay, so yeah, so this again, this UF applied to this Walshada mod of this ket of 0 tensor power m and then tensoring it with ket of 0 tensor power k. This will again appear time and again. So I'll just state it here and then keep recalling this over and again when you discuss the algorithms. So what it does is you take this UF of this 1 by square root of m summation x is equal to 0 to 2 to the power m minus 1 ket of x, which is the usual uniform superposition. So that if this in the second meaning second argument you tensor it with ket of 0, so that will give you 1 by square root of m, the uniform superposition tensored with 1 by square root of m summation x is equal to 0 to 2 to the power m minus 1 ket of x tensor with ket of f of x. So you see that in some sense you are computing the f of x for every possible x. So if you have a m qubit system, you are looking at meaning x is equal to 0 to 2 to the power m minus 1 ket of x tensor with f of ket of f of x. Okay, so you can think of this as simultaneous computation of f on all the inputs of x. So this is the first step in any quantum computation. So which is saying that meaning whether you're doing it or not, you can at least explicitly write down in terms of symbols the answer to the value of f of x for every x. Okay, classically in the quantum domain. Okay, so you're looking at ket of x tensor ket of f of x for all possible x via this UF map on this uniform superposition tensor O. So this is again going to appear everywhere in the future discussions. Okay, so this is about the basics. So I just want to take 2 minutes and then point out that there is something called the Walsh-Hadamard transform, so which is operating on 1 qubit like this, and then there is a natural way of extending it to tensor products. We have already seen this for arbitrary linear transformations. So the tensor power of meaning n w tensor power n is represented by this wn. So when we apply wn to this ket of 0, 0, 0 vector, it gives a uniform superposition of all the vectors. That is bullet number 1, which is very important. And there is a easy computational formula for computing the meaning the n-fold Walsh-Hadamard transform, which will be given by this 1 by square root of 2 to the power n summation k equal to 0 to the power n minus 1 to the power x dot k ket of k. So x dot k we saw was the dot product of 2 bit vectors. Okay, so you take the bit representation of x, bit representation of k, the usual meaning x dot k. That is what is appearing in the exponent. And then there is something called the standard oracle. So it will have various names meaning it's not difficult to see that it is unitary. So which is operating in this way. So m bit to k bit classical function. For that you write a meaning quantum oracle. It is going to operate on a 2 power m qubit tensor to the power k qubit vector space. So that is defined as ket of x tensor y under UF will be mapped to ket of x tensor y XOR f of x, where this XOR is the usual bitwise XOR. So recall that that was the motivation for looking at integers from 0 to 2 to the power n minus 1. So the output is a n classical bit string. So we can define the usual bitwise operations. So this second argument is ket of y direct sum f of x, which is just bitwise XOR of these two strings y with f of x. Okay, so the upshot is that we can simulate any classical function on a quantum computer, and there is this first operation is usually applying this UF to the ket of 0 tensor power m in the first argument, and ket of 0 and then taking the tensor product of it with the ket of 0 power k. So usually one will be called the meaning auxiliary register and one will be called the input register. So or the computational register and the input register, something like that. So we'll come to that later. So that will give you in some sense a linear combination of the argument times the value for all the possible inputs x, right? So 1 by square root of n. So 1 by square root of m summation x is equal to 0 to the power m minus 1. Ket of x tensor with ket of f of x. So in some sense, you can think of this as a simultaneous computation of f of x and all the possible inputs. Okay, so this is the first step in all the quantum computation scenario. Okay, so yeah, so we have about 25 minutes more. Okay, so first algorithm is the Deutsch algorithm. So what this does is that um, so the first thing we have to kind of understand here is that we are talking about query complexity. So what I mean by query complexity is the following. So what we have to do is that, so usually in the all the algorithms which we are going to discuss now, so except possibly for star, I think all of them do not talk about this oracle. So there is this classical function. We don't know how efficiently it can be implemented on a quantum computer, but whether it is polytime, whether it is a small circuit, whether the unitary is computable in polytime and so on, that we do not argue about. So what we argue about is the query complexity. Okay, so there is a quantum oracle which is computing some function. So usually it's that U sub f. So the query complexity refers to the number of times we appeal to this oracle. So we will ask for the value of something and get back the answer from this query. So from this oracle. So oracle is something like a black box, you can think of it, which is implementing this U sub f. So you will be querying that black box and getting back the answer to that, and no justification is given about the implementation of this oracle on a quantum computer. So whether it is efficiently implementable using quantum gates and all that, we are not bothered about right now. Okay, so what we are bothered about is that we should make polynomially many queries to that oracle in the best scenario, and whether we can make less number of queries and still get answer. So that is the kind of questions we are going to answer now. So it's not about the efficiency of implementing UF. It is about the query complexity. It's not about how efficiently we can implement UF. It is rather about how many queries we are making to this black box UF. Okay. So Deutsch gave the first algorithm to demonstrate that there is a speed up while passing from classical to quantum. Okay, so I just put that the speed up is not in terms of circuit complexity, but in terms of the query complexity. So whether we can do a certain classical computation by making less number of quantum queries to this U of oracle rather than in the classical case. So if you are making n queries in a classical case to answer certain problem, can we make lesser number of queries in the quantum sense and still get the answer? That is the kind of question we are going to answer. That is a sort of question which Deutsch answered. Okay. So meaning I'm sorry about this resolution of the picture, but it is clear what is going to happen here. So you read from left to right. So there are two wires. So you can think of this as yeah, place where we have a m qubit system and a k qubit system. So recall that the second or the third postulate, the second postulate says that if you have a m qubit system and the k qubit system, then the tensor product Vm tensor Vk is the state space for this consolidated system. So if you take this first wire, you are inputting 0 here, computing a Walsh-Hadamard of this m qubits, and then you are kind of taking it as the first argument for your U of oracle, and the second wire has ket of 0 as the input, namely y, and that becomes the second argument for your U of f oracle. And then we know that it is going to give x and f XOR f of x. So I'll just say that this is the usual XOR, and this is what is represented by this circuit. Okay, so this is the circuit which is implementing quantum parallelism. So we saw that quantum parallelism means you take this ket of 0 power m and tensor power m, apply the Walsh-Hadamard on it, and the second argument is the usual ket of 0 power tensor power k, right? K qubits. So the first one is the x input, second one is the y input. So when we apply UF to this, you get x tensor y, the ket of x, ket of y XOR f of x, right? So the final state of the system is, we saw that it is 1 by the uniform superposition, 1 by square root of m, summation x is equal to 0 to the power m minus 1. You are computing the meaning ket of x, tensor ket of f of x. So in some sense, you're computing the value of f of x for all the inputs. Okay, so this is the quantum circuit which is going to implement this U of oracle circuit, in the sense that meaning, so it's actually capturing the operation modulo, like we do not talk about how this U of is implemented. So this U of acts as a black box. So whether this y or f of x can be efficiently computed in the quantum sense, it's not. Okay, so this U of is in the black boxes. That's all. Okay, so this is a circuit which implements this U of oracle. So meaning, let us we'll be seeing this time and again later, but let us just register that in some sense we are computing the output of each of these inputs x. Okay, and meaning we can also talk about kind of putting the Walsh mod for the other qubits, other system also. So first of all, you take 0 tensor power m. On the second wire, you take 0 tensor power k. So for each of it, you compute the Walsh mod, and then you pass it down to this UF. So you can take this meaning out. You can easily compute the output and then write it down explicitly also, but I'm not going to do it. Meaning it's done here, so you can just skip this, and it is not really important right now. Okay. So let us come to this Deutsch problem. So what does this problem say? It is saying that suppose you are given a Boolean function f from 0, 1 to 0, 1. So we know that it is constant if f of 0 equal to f of 1, and it is said to be balanced otherwise. So you see that 1 is going to appear on the image and as well as 0. So either the Boolean function is constant or it is balanced. So given such a Boolean function, you want to determine whether it is constant or balanced, right? So classically, what do you have to do? You have to compute 0, you have to compute 1. The query complexity is 2. So you need to actually meaning ask this f to give the values of both f of 0 and f of 1. Only then we can compute, we can compare whether f of 0 is equal to f of 1 or not. Okay, but we can see that meaning Deutsch gave a first algorithm which says that a quantum computer needs only 1. So a quantum computer can decide whether this f is constant or balanced using just one appeal to this U of black box. Okay, so that is what is Deutsch problem. Let's just see how it does it. So what you do is that you have two 1-qubit systems. So this is the circuit. So you pass 0 in the first qubit and 1 in the second qubit, apply Walsh mod, and then appeal to this UF, and for the you dump the second qubit out, second output, and you just pass the first qubit output through W, and then you measure. Okay, so let us see what this entire circuit is going to do. So two 1-qubit systems. First one pass 0, second one pass W, and then take the Walsh mod of both these 1 qubits, and then pass this output through UF, dump the second output, the second register, and take W for the first register and measure it in some sense. So we'll just come to what happens later. But this is what we are going to do. So let us just write it down. So we are computing W. So we again know that the combined the quantum mechanical system is going to operate on the tensor product of this W. So if you associate W with the first 1-qubit system and the same W, actually it's in some sense it's the same vector space, right? So W to the second qubit system. So we have W tensor W, that is where this entire 2 qubits are going to operate. So if you look at this W tensor W of this ket of 0, ket of 1, so you can write it as this. So 0 will go to ket of 0 plus ket of 1 by square root of 2. 1 will go to ket of 0 minus 1 by square root of 2. So you take the tensor product of these two things. So it is easy to verify that if you then take this and apply UF to it. So I'll just leave this as an exercise for you. So take this, take the right hand side of this thing, and then you apply UF to this. So you will get minus 1 to the power f of x, ket of 0, tensor with ket of 0 minus 1 by square root of 2. Okay, so here x is a bit 0 and 1, right? So we see that after the state the state of the system after passing through UF. So what we get is that it is 0 ket of 0 plus ket of 1 by square root of 2 tensor with ket of 0 minus 1 by square root of 2 if f is constant, and it's plus or minus this if f is balanced. So if the first qubit measures to 0 with probability 1, we say that f is a constant, and if it measures to 1, we say that it is balanced. Okay, so if the first qubit measures to 0, respectively 1 with probability 1 in the computational basis, then we say that f is constant, respectively balanced. So we see that this is involving only one appeal to this UF oracle. So with one appeal to this UF oracle, we can get distinguished between this constant versus balanced. Okay, so which is an improvement over the classical case, which is requiring two appeals to the f function. Okay, so we can extend it to the problem which Joshua kind of addresses is that it is going to extend this Deutsch problem to the n-bit system. So you have a Boolean function which is from z2 to the power n to z2. So we have strings 0, 0, 0, 0, 0 to 0, 0, 0, 0, 1 and so on till 1, 1, 1, 1, 1. So with this we are associating the 0, 1. Okay, so f of 0, 0, 0, 0 is 1 or 0 like that. So if there are equal number of ones which are appearing in the image side as equal number of zeros, that is to the power m minus 1, we say that the function is balanced. Otherwise the function is not balanced. Okay, and the problem which this is going to be addressing, this Joshua, is it's going to either tell that the function is balanced or it is going to say that it is going to be a constant. So these are the only two options it will give. So it's not going to say whether it is not balanced. Okay, so given a Boolean function, you decide whether it is balanced or a constant. So you have to tell this. So what is going to happen is is being captured by this Joshua. So actually the first bullet is a mistake. So this is the extension of Deutsch to multivariate Boolean functions. So the classical thing requires 2 to the power m minus 1 plus 1 evaluations, right? So if you see that you make after this, you see that there are you again get either a 0 or 1. We say that it is balanced. Otherwise, we say that it is a constant. Okay. The quantum requires one evaluation of the oracle. So you have to make 2 to the power m minus 1 plus 1 evaluations in the classical sense. But in quantum, you are going to just make one evaluation of the oracle. So this is the circuit. So what you do is that you have a m qubit system on the first wire and a 1 qubit system on the second wire. So you take ket of 0 tensor power m, you apply Wm, and then in the second wire you take this ket of 1, you apply W, you pass these through two things to this UF oracle, and then you dump the second one, take the first one and send it through Wm, and then you measure it. So we can see that after passing through the Walsh-Hadamard gate, this Wm tensor W, you are applying it to ket of 0 tensor power m tensor with ket of 1. We see that we are in 1 by square root of 2 to the power m summation x is equal to 0 to 2 to the power m minus 1 ket of x tensor ket of meaning W of ket of 1. So this is the meaning state after passing through Wm tensor W. So after applying UF, meaning it can be verified that you will get this 1 by square root of 2 to the power m summation x equal to 0 to 2 to the power m minus 1 to the power f of x ket of x tensor with W ket of 1. Okay, so here there is this definition of this d of f. So you take the whatever is appearing. So notice that this W ket of 1 is independent of this x. So in some sense the linearity will kind of throw it out. So you look at this d of f, which is some 1 by square root of 2 to the power m summation x equal to 0 to 2 to the power m minus 1 to the power f of x ket of x, right? So with each ket of x, you have a minus 1 to the power x f of x is sticking to it. So either it is 1 or minus 1. So whenever the answer to f of x is 1, you get a minus amplitude for this ket of x. So that is what this is doing. So when you apply W, so we are just meaning following this thing. So you're applying Wm to this output after this UF. So you're discarding the second qubit. the second register, and then you are taking the WM of this D of F, we see that we are getting this double summation. So if F is a constant, applying Walsh-Adam mod to D of F and measuring with respect to computational basis will give you 0. So we can see that that is going to happen. If F is balanced, we never measure 0. Since the coefficient of meaning ket of 0 is 0. So there is a simple exercise here. So if F is constant, with respect to computational basis, after applying that meaning m qubit Walsh-Adam transform, you will be measuring 0 in the computational basis. And if F is balanced, we will never measure 0 because this ket of 0 will appear with coefficient 0 after meaning expanding this kind of a linear combination. Okay, so two cases we can decide by just meaning doing this kind of a computational algorithm. So we'll just skip this. So I just want to, so next, so we have not even touched to Grover or Simon or Shaw. So tomorrow we'll be doing all three of them. So the main thing I want to point out is that please remember this D of F. So that is going to, for whatever, so if you have this F, which is a classical function, so D of F is defined as 1 by square root of m summation x is equal to 0 to 2 to the power m minus 1 to the power f of x, get of x. So in some sense, so wherever x is wherever this get of the classical function x is going to be not 0, this will appear with a negative sign, and wherever it is going to be 0 will appear with a positive sign. Okay, so so the Grover will manipulate this amplitudes of D of F. So Grover is actually a such problem. So we'll be searching for a certain string in a domain. So what will happen is that we'll be meaning doing the standard Walsh-Adam mod and then applying this UF coming to us register coming to a state and then isolating this D of F function, and we will be applying, sorry, the Grover will be applying some mechanisms for increasing the amplitudes of this. So this will be meaning what Grover will be doing will be increasing the amplitudes of this desired values. So so the upshot is that remember this DF and then remember the mechanism of starting with certain qubit systems, applying Walsh-Adam mod on it, and then this UF is universally capturing the classical computation in the quantum sense, and then the meaning operation will proceed as you take this meaning you'll be taking the Walsh-Adam mod and then applying a suitable UF on it, and then you'll be measuring something. So this is what is going to happen in all the three kind of algorithms which I plan to do next, namely Grover, Simon, and Shaw. So that is that for today. So if you have any questions, I'll be happy to answer.
Sir, you are able to hear me?
Yeah. Tell me. So I was online, right, throughout?
Yes, sir. You are online.
Thank you.
Sir, this is Dr. here. Sir,
Sorry?
This is Dr. Atisha here. Sir, I have a simple doubt, sir.
Yes, ma'am.
You have explained a number of quantum algorithms. So
yes.
How to choose the appropriate algorithm for a particular cryptographic key?
Okay, so meaning usually, so what you mean is like you want to say attack RSA. So in that case, the underlying problem is factorization, right? So there you'll be applying Shor algorithm. Okay, number one. And if you want to attack, say the discrete log or a Diffie-Hellman kind of a problem, there again you'll be applying Shor algorithm. And if you want to do some kind of meaning attack on a symmetric key crypto system, then you'll be applying, say, a Simon or a Grover algorithm. So mainly Grover algorithm, where you'll be searching on an unstructured domain. So you'll be having plain text, ciphertext pairs, all of them encrypted with the same key. So you'll be searching for that key. So the more suitable thing in that scenario will be Grover algorithm. But meaning there are a lot of advances these days. So For example, in the post-quantum sense, so if you are talking about, say, for example, this supersimilar isogeny, so there is this graph problem called claw finding. So for that, the people use Tani algorithm. So TANI, Tani's algorithm. And so there is a huge class of problems called hidden subgroup problem. So that is the key to solving many such cryptographic meaning challenges. So the hidden subgroup problem is having a quantum solution. So that becomes key in the cryptanalysis sense. And meaning mainly these are the ones which I know. So Grover, yes, for attacking your symmetric key, and Shor for attacking RSA and Diffie-Hellman, and the hidden subgroup problems has on the quantum algorithm to that problem has a lot of impact on a lot of cryptanalysis problems. Yeah, that is the answer. Yeah.
Thank you, sir. Thank you.
So, meaning I'm sorry for deviating from the schedule. I thought that I will go through all these things and then kind of come to a place where meaning we have defined the standard first steps for all three of them. So the things are going to vary only after this, meaning on a case-to-case basis. So up to this, like starting with certain qubit systems and then applying Walsh-Hadamard and then this UF Oracle. So this is going to be standard for all the three of them, namely Grover, Simon, and Shor. And the kind of efficiency and polytimeness will vary. So Grover, we don't know what will happen, but Shor, you can say that there is a I'll not be covering it, of course, but there is a standard argument that you can implement that UF oracles efficiently in the case of Shor. So it's going to be polytime computable in some sense. So you can actually describe a quantum circuit which is implementing this Shor, as far as I know. Yeah. So meaning unless so if you have a black box kind of a description, it's not clear how to get a UF corresponding to it. But in the case of Shor, the main problem is that of period finding, which is going to depend on this quantum Fourier transform. And meaning I see that there is an efficient quantum circuit for implementing this quantum Fourier transform. So in some sense, we can describe a circuit which is going to do this Shor algorithm. And meaning I'll not be going to depth on up to that level, but I just want to say that the initial steps for all the three algorithms I've just covered. Now, how the three algorithms proceed and kind of solve the intended problems, that will be covered tomorrow. And I'm sorry that this Shor will be very short. Like the Shor algorithm, it's pretty involved, and I'll just give the main bullets in it and leave some of the parts of it for you to learn and verify. Okay, so that will be the schedule. Like tomorrow we'll start with Grover, then quickly we'll finish off Simon and then go to Shor. And I'll give the outline of Shor and ask you to fill up most of the details. That will be the plan for tomorrow. Yeah. I'm sorry, ma'am, you're not audible.
Yeah, I'm audible, sir. I'm audible, sir?
Yeah, you're audible now. Yes, ma'am. Yeah.
So thank you, sir. Thank you very much for your elaborate presentation on the vector space for quantum computation. Also, you have given the basics of so many mechanical systems, quantum mechanical systems, quantum parallelism, and algorithms like Deutsch and Grover algorithm. So actually, tomorrow we have one more session. So I request all the participants to interact with the sir, and you can clarify all your doubts in the next session too. So thank you very much, sir.
Thank you. Hope it was useful. Thank you. Thanks.
It was so useful, sir. Even I was completely sitting throughout the session along with the. Thank you, sir. Thank you very much, sir.
Thank you, ma'am. See you. Yeah. Bye. Tomorrow, 10 o'clock. Sure, ma'am. Yeah.
Sure, sir. Thank you, sir.
Thank you. Bye.
audience. Participants are requested to stay in the line for the next session.